So, if we have a wire loop with a current going around it, we can calculate the magnetic field. We've already done so along the axis, but you can do it numerically everywhere. And what you find is a field that looks something like this. Now this might look familiar. If you've ever played with permanent magnets, little bits of iron at school, sprinkled iron filings around them, this is the sort of pattern you get. This is indeed the magnetic field of something like a permanent magnet. It's also very much like the magnetic field of the Earth, with the Earth in the middle here. So you get a bar magnet with a north and a south pole, or the Earth, which effectively has its north pole at the south and the south pole at the north. It's a bit bizarre the way the Earth works, but basically the north pole of your compass points towards the north pole of the Earth, which means the north pole of the Earth is actually the south pole if you imagine the Earth as a giant magnet. But this whole pattern is called a magnetic dipole and is an extremely common one. That's not a coincidence. The reason why you get this pattern comes down to individual atoms. Now, an atom consists of positively charged nucleus and negatively charged electrons moving around it. Now, as you may know from chemistry, these electrons are in orbital patterns, which are rather complicated, which we'll learn more about in quantum mechanics in later years. But in some atoms, including iron, some of the electrons are effectively moving in orbits around the center, much like planets orbiting around the sun. So what that means is you get charge moving in circles, which of course is very much like a current going in a loop. If the electrons are going this way, then effectively that's a current going the other way, so you'll get a magnetic field something like this. And indeed, individual atoms, in fact even subatomic particles can do this, act like microscopic wire loops. They have a magnetic dipole. How does that help you with a bar magnet? Because a bar magnet has a lot of atoms. Now, if you have two magnets, say one with a north pole and one with a south pole here, but they're close to each other, they will tend to line up in opposite directions, because unlike poles attract each other. If atoms do that, which is indeed what they do in most materials, then one will be pointing up, one will be pointing down, one will be pointing up, one pointing down, and so they'll pretty much cancel each other out. However, ferromagnetic materials, in particular iron, have the rather strange property that the electrons in these particular orbitals tend to have a force, an electrostatic force, not magnetic, to nearby atoms, which causes them all to line up in the same way. It makes it most energetically favorable. So in these materials, and only these materials, you can get permanent magnets by getting all the magnetic moments, which is effectively the spinning currents of the individual atoms, lined up together, pointing in the same direction. This tends not to happen over an entire magnet. If you have a big bar magnet here, what you tend to get is regions called domains, where everything is lined up. Then a different domain where they've got some different orientation, and so on and so forth. Why does this happen? Well, this force that makes the atoms line up with each other is a very short-range one. So while it might help this atom and this atom line up, it won't have any effect on the ones over there. On the other hand, the magnetic field is rather longer ranged, so it tends to mean that on longer scales these things like to be in opposite directions. So you tend to get lined up on short scales and anti-lined up on long scales. But you can make permanent magnets and get the different domains mostly to line up, and that's how you get the bar magnets that you stick on your fridge and the like.